Okay, so first of all, I would like to thank the organizers for inviting me to this very special conference. As I just said, I was actually a postdoc working with Hubert in Los Angeles between 1999 and 2002. And I would like to say that Hubert was actually an excellent teacher, mentor, and role model. And I would like to thank him for this. And of course, happy birthday, bon anniversaire, and many happy returns. So today I will talk about a subject that is a little bit different from the previous subjects, but I think it's actually a really beautiful story. It's about theory of materials formed as complements of triply periodic constant mean curvature surfaces, and it's at the same time a very amusing story. So these are the reference. The work was done in collaboration with Ralph Kaufmann and Sergei Klepnikov at Purdue. And there are actually 7 papers, and the last one was published only last year. So I think it's still fresh in our memories. It's a very funny starting point of this project because it started with an initial phone call by Hugh Hillhouse, who at the time was a chemical engineer at Purdue, and he called us up on the phone asking if we could tell him something about the structure of this double gyroid, which is a wonderful mathematical structure. And the hope he had at the time was that this would make solar cells more effective. And I think this has been answered negatively since then. But still, there's a new prospect, namely that we can discover special properties that are driven by topology. So this is actually a subject that is pretty a la mode at the moment and very interesting. So we will concentrate on the channels of the gyroid surface, and this will become clear in a moment. So this is the outline. It looks a lot, but it's actually, I will be able to finish in 35 minutes, hopefully. So they're basically an introduction that talks about the gyroid and the fabrication. So with some experimental slides, and then I will talk about the theoretical description, some general results, and then I will focus on points where we have degeneracies in the spectrum, where we find new Dirac points. We can explain them in terms of enhanced symmetries. And the last part is about topological charges. So this is the structure of the gyroid. It's actually a triply periodic surface in 3D that is embedded in R3. And so it goes on in all 3 spatial directions. And it has this very complicated structure and has these channels that wind through the surface. So it was discovered only in 1970 by Alan Schoen. As I said, it's a triply periodic minimal surface. And surprisingly, it appears in nature on certain wings of butterflies or beetles. And it consists actually of 2 mutually non-intersecting embedded gyroids. It has this large symmetry group that is given by this notation over here. And it mimics or it describes the geometry of a thick surface. So to plot the pictures I will show you, you can use a level surface approximation that is given by this formula over here, where we have families of surfaces parameterized by LT and L minus T that are given by this formula, but this is only an approximation to plot these pictures. And what we are going to concentrate on are the channel systems that wind through the surface. So the voids of the picture are actually made up of 2 non-intersecting channel systems. So you see this better in this picture. You see this thick surface that is made up of, well, basically 2 surfaces and the space filled in between. And then we have these channel systems that wind through the voids. And if you analyze them, you will actually see that there are 2 different intertwining channel systems that can be found in the voids of the surface. So it's incredibly complicated. Nevertheless, it appears in nature on the wings of these butterflies, for example. And you see in this electron microscope picture that there are indeed gyroid photonic crystals that are responsible for the vivid colors on the wings of this butterfly. So there are gyroid structures for these butterflies, and there are also diamond structures that can be found on certain beetles, and I'll come back to these diamond structures in a moment. So it's quite surprising that these already exist in nature. So let's go back to physics. This shows a unit cell with these two channel systems that I talked about, and we will in the following just pick one of them because they are equivalent. And we will concentrate on these channels. And it turns out that they can actually be fabricated in the lab. So this was also, they were also studied at Purdue. So this nanostructure of the double gyroid can be synthesized by self-assembly. Because it's a minimal surface, it self-assembles with a lattice constants of 18 nanometers. And then the voids can actually be filled and the surface can be removed to form a structure of these channels. And this can actually be done with certain semiconductor materials. And I even have some experimental pictures, which I'm always very proud of if I give a mathematical talk. So you see some Bragg pictures here that help to characterize the symmetry, and you see some electron microscopy images. So I won't go too much into the details because of time, but it's a real material on the nanoscale. So how do we go about describing this? Well, if we concentrate on one of these channels and we look at the elementary cell, we see that there's actually a skeletal graph inside these, this channel that we can deformation retract onto. And there in an elementary cell, there are 8 vertices that are labeled from V0 to V7 here. And we can take away the channels and concentrate on this graph. And this is what we are going to do in the following. So the first step is to look at the quotient of this. Well, it's an infinite graph because it's periodic in all directions, but we can take the quotient of by the translational group Z3, and we end up with a cube, which is quite surprising, but you see that at every vertex there are 3 edges going out. And if you follow the structure of this and you mod out by the symmetry group, you see that you get a cube, still with 8 vertices. And then this is not the full symmetry, actually. The full symmetry is given by the body-centered cubic lattice group. And if we mod out by this lattice group, we actually get this structure, which is a tetrahedron or a full square, which we get from the cube by identifying opposite corners. So the vertex 0 is identified with 6, 1 with 7, and so on. So in this tetrahedron, we can also show that there is or we can also represent it as a rooted spanning tree where we have edges going out from this root that is sitting at the left lower corner, and we can represent it like this as a diagram where we show the loops on this tetrahedron. So how do we go about studying this theoretically? Well, we chose a method that was proposed by Belisard in non-commutative geometry, because we also were interested in putting this gyroid in a constant external magnetic field. So we define an abstract C-star algebra that consists of a Hamiltonian that we're going to describe and the symmetries of the system. And the Hamiltonian is the usual Harper Hamiltonian, which is a tight binding model, which is written down here as a sum of the translations along the edges of this graph. So we sum over the edges and taking into account their direction. And the point is that if we put this gyroid into a constant external magnetic field, these translations do not commute anymore. So we have to do calculations in non-commutative geometry. So the strategy is to study this algebra that is made up of the Harper Hamiltonian and the symmetries. And it turns out that in the commutative case, this classifies the geometry of the Brillouin zone. And of course, we would like to understand the spectrum and the physical properties. So I would like to talk about some general results that we have obtained first, but only very briefly. So we have obtained an analog of a gap labeling theorem that is very close to the Hofstadter butterfly in 2 dimensions, but this is now a 3-dimensional structure. So we can show using K-theory that if the entries of the magnetic field are rational, there are only finitely many gaps in the spectrum of H. And if the magnetic field is irrational, there might potentially be infinitely many gaps. So we get a structure that's very similar to the Hofstadter butterfly that is shown here, only that the lattice constant now is much larger. It's 80 nanometers, so the B field is reasonable, and it might be possible to detect this experimentally. We were also able to classify this algebra, this abstract algebra that we have defined, and it's basically, in most cases, given by the non-commutative 3 torus. Only there are some special values of the magnetic field, which we can give explicitly, but I won't give them here because it's way too complicated to show them in a short time, where the algebra is really a proper subalgebra of the non-commutative torus. If we have no magnetic field, the commutative geometry is that of a ramified cover of a three-dimensional torus, and there are some level crossings and splittings that are given by the ramification locus. So these are actually the interesting points, and we can show that in this case where we have no magnetic field, some of these points where we have level crossing and level splittings are Dirac points for the gyroid, which is new because they are Dirac points in 3 dimensions. And we have repeated the same analysis for the honeycomb lattice in 2 dimensions, which is the structure of graphene, and we recover the known Dirac points for graphene as well. So this method reproduces old results and produces new results. We were also able to show that there's a linear dispersion relation at these points, so that we are really dealing with conical points. And the question is, of course, are these topological stable? A numerical study shows yes, and later on I will show you that there's an explanation in terms of Chern classes and topological invariants that explains why these points are topologically stable. So it would be really interesting to see measurements of this. And there are Dirac points that have been measured in photonic crystals and other 3D materials. So it would be really nice to see them measured here for the gyroid structure as well. So let me give you some details of the calculation. So if we have a magnetic field, we have translations along the edges that become non-commutative, and we will express them in terms of these operators ui and uj. And these parameters theta that appear in these factors, they are related to the magnetic field, and they are given down here. And these vectors G1, G2, G3 are actually the vectors of the BCC symmetry. They are linear combinations of the vectors F I showed at the beginning. So if we use this notation, we can write down the graph Harper operator as a 4x4 matrix, because we have 4 vertices in our elementary cell that looks like this. And if we translate it now to, or if we rewrite this now as a matrix Harper operator, it looks like this, and we can abbreviate these products of operators by operators A, B, and C. And they are still non-commutative, but if we remove the magnetic field, they can be written in terms of quasi-momenta, and the quasi-momenta will be denoted by small a, b, and c. So this is the Harper operator I will talk about. And the question is, can we classify the points over the base where the Hamiltonian has degenerate eigenvalues and give them multiplicity? And if possible, identify symmetries that allow us to understand the eigenspaces. So these are the 2 following parts of my talk. The first one is answered in terms of singularity theory, the multiplicities of the eigenvalues. And the second one is answered in terms of a regauging symmetry that we found. So let me first go to the singularity theory. So this is in the commutative case where we don't have a magnetic field anymore. So the Hamiltonian is parametrized over the base torus T to the n. In this case, n is equal to 3. We look at the characteristic polynomial as a smooth function P, and we determine the critical points of P, which are the singularities. And at the same time, we will look at the signature of the Hessian to determine whether the singularities are indeed conical. So if the signature of the Hessian is minus, 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 plus, we indeed find a conical singularity. actually we look at this what we call the characteristic map. So p to the -1 of 0, which is the point where we have the singularity, is the pullback of the universal unfolding of the ak-1 singularity along the map that is given by the coefficients of p considered as a polynomial in Z. So this is what we call the characteristic map. And this lets us read off the type of singularities. And in fact, the singular points are the inverse images of the discriminant locus. So the discriminant locus is the locus of all points where degeneracies can occur, right? If the discriminant is equal to 0, these are the points where we have degeneracies. And the type of singularity pulled back to the fiber is then given by the respective stratum of the unfolding. And this is due to a theorem by Grothendieck. So let me summarize the results first, and then I will give you some pictures. So we did this for 2 different cases, for the honeycomb and for the gyroid. So in the honeycomb case, we find the 2 degenerate points in the spectrum that are the Dirac points. And we can show that these correspond to enhanced classical symmetries. For the gyroid, we find 4 degenerate points. 2 of them are triple degeneracies, and 2 of them are 2 double degeneracies. And only these 2 double degeneracies are actually Dirac points. The other ones are not. And we can also find enhanced classical symmetries. So this is what we did as a calculation. You see the characteristic polynomial as a function of the quasi-momenta ABC. And the coefficients A1 and A0 are given here explicitly. So you see the A0, A1 diagram over here, and this line that is given over here is actually the discriminant locus. So it's the locus where the discriminant is equal to 0, which means that all degenerate points in the spectrum have to touch this line. And this blue shaded area is the area that is filled by points that you obtain if you vary A, B, and C between 0 and 2 pi in the A0, A1 plane. And you see that this blue shaded area touches the discriminant locus only in 3 points, which leads to these 3 degenerate, well, actually 4 degenerate points, because you traverse this figure back and forth. So you start here if you vary A, B, and C, and then you touch this point, you go up here and you go back. So this point is actually touched twice. So we find 4 degenerate points. And there are actually 2 cusps that are in the stratum of type A2 singularity, and a double point that is in the stratum of type A1, A1. And if we look at the fibers over these points, they are all discrete. For the A2 singularities, we find 1 point each, and for the A1, A1 singularities, we find 2 points each, which explains the crossings in the spectrum. So let me show this in the spectrum. So this is the band structure, and it's given for the particular choice along the diagonal where A is equal to B is equal to C. And you find that there are actually 2 triple crossings, while this one over here and this one over here for 0, 0, 0 and pi, pi, pi. And then we have 2 double crossings at pi over 2, pi over 2, pi over 2, and 3 pi over 2, 3 pi over 2, 3 pi over 2. So we were able to explain these crossings in terms of singularity theory. There's also the question if we can explain these in terms of symmetries of the underlying graph. So that is always a very natural question, where the underlying graph has symmetry group S4, and a priori it's not really clear how to get 2-dimensional representations. So what we discovered is that there's actually a regauging that we can use on the Hamiltonian, and that can be lifted as a conjugation of matrices, and then we can look at the representation of these matrices, and we can identify non-trivial stabilizer groups. So in order to do this calculation, we look at the action of S4 on T3, which is fixed once we look at these elementary permutations, 1, 2, 2, 3, and 3, 4. And then we can calculate graphically, so we can go back to our rooted spanning tree with the 4 vertices. And it turns out that this regauging symmetry consists consists of multiplying either the vertices or the edges by some factors. So if we permute the vertices 1 and 2 in this original diagram, we get this shape over here. So the vertex number 2 is now down here, the vertex number 1 is up here, and we would like to get back to the original form where the root was actually at the lower left corner. So what we can do is we can multiply by these factors. So we multiply the vertex number 3 by a factor A and the vertex number 4 by a factor B star. And you can show that this is equivalent to multiplying the edges accordingly. So we can pull these factors back onto the edges. And so the factor A and B star become a factor A and B along this edge. And this factor A cancels this A up here. So we change the factors that we have on these edges. And now we see that we have again a rooted spanning tree, which with ones on these 3 outgoing edges of the root. And we can actually just rewrite this diagram to obtain the original form back, but now the factors have changed on these edges. And the transformation that we have just calculated consists of this transformation where ABC is actually mapped on A star, B star, ACB. So this is the calculation for the action that permutes 1 and 2, and we can do analogous calculations for the other permutations, and then look at the representation theory of these regauging transformations. And what we find is that there are different results for the different points where we have degeneracies in the spectrum. So for 0, 0, 0, it's the most boring case. The regauging matrices give the usual representation of S4 and C4, which decomposes into a trivial representation and an irreducible 3-dimensional representation. This explains the 3-fold degenerate eigenvalue at 0, 0, 0. At the point pi, 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 we only get a projective representation, but we can rescale by a 1 cocycle and find again the 1-dimensional trivial representation and the 3-dimensional standard representation. However, at the points pi over 2 and 3 pi over 2, which are the interesting points because they are the Dirac points, we find a projective representation of A4, and after scaling by a 1 cocycle, we find a representation of 2A4, the binary tetrahedral group. And this indeed has 2-dimensional irreducible representations, which explains the degeneracy of 2 that was not present in the original symmetry of the graph, if you just consider the symmetry to be S4. So this is very insightful. So the last chapter of the talk is about topological charges. And you see a summary of our results in this view graph over here. So you see on the left-hand side a numerical study that Sergei Klepnikov did, where we have defined certain topological charges that I will explain in a moment. And you see, well, S is actually, it's a little bit obscure. S varies between 0 and 1, but it's really the Brillouin zone. So it's really varying between 0 and 2 pi. And you see that there are 4 different topological charges, and they jump around if we traverse the Brillouin zone. And what actually happens is that if we traverse, you see a picture of the 3-dimensional Brillouin zone here with the singularities on the diagonal. So if we go through the Brillouin zone along the diagonal, every time we cross a singularity, these topological charges jump in a certain way. And the idea is to derive this from general principles and to explain this, this phenomenon that we saw numerically. So this is actually a study of the bundle geometry. So we have a trivial vector bundle that is the torus cross ck, where k is equal to 4 because we have 4 vertices. And we denote by T degenerate the locus of points where the Hamiltonian has multiple eigenvalues, and T0 is T without T degenerate. So if you look at T0 cross Ck, this can be written as a direct sum of eigenbundles, and on these eigenbundles you can actually calculate Chern classes or Chern numbers that are the charges corresponding to the Berry phase. and they are obtained as an integral over the Berry curvature. So this was already found by Berry and Simon. So let us again look at the two cases that I talked about previously. So if we are in 2 dimensions, the torus is 2-dimensional compact, and then the Chern classes are just given by the integral over the Berry curvature. So this is what happens in the quantum Hall effect, where you have these TKKN numbers. So the torus here is just T0. There's no degenerate locus, no degenerate part of it. However, if the degenerate part is not equal to 0, then automatically all the charges are going to be 0. And this is the case for graphene, where we have 2 degenerate points. And therefore, we can say that the Dirac points in graphene are not topologically protected. However, in 3D, the situation is very different, because we have to pair with a second homology group. And there's actually a very nice method to encode this, and this is called slicing. And it uses the method that I've already showed previously, where we look at these slices between the singularities, and we try to compute charges on these slices, and then look at the jumps if we go from one slice to the next. So this is a mathematical description of this method of slicing, where we have projections in each of the 3 directions, and we have inclusions that go the other way around, and then we can define the charges that we calculate as the integral over these numbers, these charges computed on the eigenbundles and then pulled back via the inclusion. If we hit points in the degenerate part, we set the charges equal to 0. So there are also definitions for higher dimensions, but I will not talk about. So the idea is, again, to compute these charges on these slices that are 2-dimensional, where we can do this, and then compute the difference in charges once we go across the singularity. So we have local charges or local jumps. We can actually look at them as being integrals over a sphere that encircles these singularities. And we can actually calculate them as Chern numbers. And there's actually a local model that was written down by Berry and Simons that describes how this crossing looks like. And this local model is just given by the product of X and L, where L is the k-dimensional representation of spin M, and then the local charges would become the numbers between or the integers between -m and m. So by Stokes' theorem, we can indeed say that we can integrate this, or that we can write this integral over the sphere as the difference of the 2 Chern numbers, or the 2 topological charges on these 2 slices that are below the singularity and above the singularity. So by Stokes, we can actually rewrite this integral over the sphere as the difference between these 2 numbers. And the question is, can we find local models? So for a double crossing, the above model is the only model, but what can we say about higher degeneracies? So can we actually find global properties, which means can we say something directly about the charges? So for example, we know that the sum of all charges has to be 0. And if there's a time reversal symmetry, we know how these charges are related by time reversal symmetry. So in other words, can we say something how the local models determine the global structure, and can we say something about the behavior under permutations? So this is a definition of what we call a spin type model. So we say that the Hamiltonian that we're looking at is of a certain spin type model at the point where we have degenerate eigenvalues. If we can write this formula in first order perturbation theory, where P are the projectors onto the degenerate eigenspaces of the 2 Sj plus 1-fold crossing, and then we have a linear term and a term that is given in terms of the spin Sj representation of SU2. And then we would actually call the local charges M, where M is given by this expression over here, and we will also identify a sign that we can call chirality. So if we apply this definition and make the calculation for the gyroid, we actually find that for the 3 or for the 4 level crossings, we have different crossings of different spin type. So at 0, 0, 0, we have a spin type 1, 0 with a chirality of 1. At pi, 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 a spin type 0, 1 with chirality -1. And at the Dirac points, we have at both points a type 1/2 and 1/2 with chirality -1 and 1. So we can classify all these singular points, and we have identified global constraints that give us some properties for these charges. So we can show that these charges are locally constant outside of the singular points, and that they have to be step functions with integer values. So these charges have to be all integer. And from time reversal symmetry, we can constrain them with a certain type of symmetry. And then there's also an extra symmetry if you translate the momenta by pi, pi, pi. There's the symmetry that is written down here, and that constrains additionally the values of these topological charges. So if we take all these global constraints into account, we can actually start a calculation where we derive what these local charges have to be. This is a little bit sketchy, so let me just go to the result. So I've changed notation a little bit in this graph. So the charges are now the chi I of t. T are the points where we have used the slicing. So the t points are between the points where we have singularities. And we have computed these charges, and you see that, for example, the charge 1 starts at -1, then it jumps to 0, and then it jumps to 1, whereas the charge 2 starts at 0, then jumps to -1, and then jumps by 2 at this point, pi, 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 to +1, and then goes back to 0. So there are these charges that occur at the Dirac points that are only jumping by 1, and there are these other charges that occur at the triply degenerate points that jump by 2. And this is exactly the graph that we have obtained numerically by a numerical study. So it is possible to derive all these charges from these general constraints and from the spin type model. And it turns out that if you go through this calculation carefully, that these level crossings are completely fixed up to only one parameter. So it's really possible to find all these topological charges from this careful study of the constraints. So this is especially powerful if we look at the deformations of the Hamiltonian. So this is the last thing I would like to show you. We have slightly deformed our Hamiltonian by changing the elements on the diagonal by some real factors R that are randomly generated numbers. And if we study now the new band structure, we see that the Dirac points are stable under these deformations, so they don't change. Their charges don't change because they are given by these Chern classes. However, the triple crossings break up into 4 double crossings, and the reason is that they can jump by 2. So they can actually change slightly. They can break up into crossings where we have only jumps by 1. So this is seen numerically. For example, there's this picture that shows you the vicinity of the triple crossing at pi, pi, pi. And you see that the triple crossing has broken up into 4 A1 points where the charges only jump by 1 and not by 2 anymore. So if we repeat this analysis for the Dirac points, you see that they won't change. So this shows explicitly that the Dirac points are topologically protected. So I'm already at my conclusion. So the gyroid is the most interesting of triply periodic structures. So we compared this to the P and D surfaces. Let me just show you this quickly. You can repeat the same analysis for the P surface, which is just the primitive or cubic surface that is given here, or for the diamond structure that is given here. And you see the skeletal graphs also in these pictures. So you can just repeat the same analysis for these skeletal graphs of these other 2 structures. And you find that they are very boring compared to the gyroid because they don't even have Dirac points. So the Dirac points, there are no points, but they are, for example, in the diamond structure, they are lines of intersection where the Hamiltonian has the general eigenvalues, but there are no isolated points. So the gyroid is the only one that has isolated points that are, two of them are Dirac points. So the topological properties can be explained analytically. It can be viewed as a 3D analog of graphene, which we always use as a reference. And we develop local models and global constraints. There should be, we showed that they are stable under deformations, and it would be really nice to see this with experimental techniques and to see if this can be observed actually in nature. Okay, thank you very much for your attention.
Well, thank you very much, Birgit. So I told people this morning that Hubert's interests were very diverse, and it's reassuring to see that those of his ex-collaborators have spread out even more. So I think that's something wonderful about physics, that somehow there's some tendency to explore new territory. So are there any questions? Hubert has one, of course.
Hello, Birgit. Nice seeing you.
Hello.
Thank you for this beautiful talk. So I see you've become a real mathematician now. So I guess I'm very naive, but it seems to me all this gyroid was just a justification to introduce a nice lattice in 3D, which had nice properties like the honeycomb lattice in 2D, namely free electrons with a magnetic field, exhibited Dirac points and all kind of things. Okay. Now, what does this property have to do with starting with the interior of a minimal surface? This is what I'm not getting. In particular, what does minimal have anything to do with the story? I mean, at the end you said, yeah, this is the only interesting minimal, triply periodic minimal surface that gives rise to nice results. I understand why you want periodic. I don't understand why you want minimal. Can you help with that?
Well, we started to study the gyroid because it was proposed to us, and I think it was fascinating that this is a minimal surface because it forms as a self-assembled, it forms as self-assembly, and that's also the reason it occurs in nature. So I think it's a part of this very special family of surfaces that are minimal. I don't think that it has any relevance for the present structure or for the present results that it is indeed a minimal surface. I think it's just a property of the original structure. I don't really think there is anything that we have exploited. There are, of course, other studies that start from the surface. So we have studied the complement of the surface. There are other studies that look at the surface and that do calculations on the surface in terms of differential geometry, and then it would, of course, play a role that we talk about the minimal surface. But we haven't really explored this direction.
Okay. And obviously there's a generalization to higher n, right? You discussed n equals 2 and 3.
Right.
The honeycomb and the gyroid, but what are these surfaces what are the lattices rather in higher dimension? What's known about them? N equals 4 saying?
Well, I'm not really sure. I'm not really sure at this point because we haven't really looked into this very much.
Okay. Well, okay. Well, thank you.
Mm-hmm.